This tutorial is about the transformation of curves, and I'm going to be using this really useful program called GeoGebra. It's free and it's easily downloadable from their website. But before we start, let me re-familiarize you with sin x before we start mucking it around. I think the first point to note is that it has a value of 0 at 0 degrees. And these are the other 2 points at 180 degrees and 360 degrees where the curve is also 0. So between 0 and 360, the curve completes one cycle. In other words, it goes away and comes back to exactly where it started from in 360 degrees. And that's known as a cycle. If I now show the turning points, now the turning points are where the curve decides to change direction. Up to 90 degrees it was climbing in value, and beyond 90 it was falling. Again here, falling down to -1 at 270 degrees, changes direction and starts climbing back up to attain 0 again at 360 degrees. So keep that shape and those points in mind as we now muck that curve around. There are 4 transformations we're going to be looking at. 2 of them are vertical and 2 of them horizontal. Now the vertical ones, I would suggest, are totally intuitive. In other words, you would have guessed what would have happened to the curve. However, both the horizontal ones go slightly against common sense, but I'll show you why they happen the way they do. Okay, let's think about vertical. What can we do with this curve vertically? Well, we can push it upwards on the axis, and we can push it downwards on the axis. Now, on both occasions, the curve won't change its shape. It will just move with respect to the axis. But if we do want to change its shape, we can stretch it vertically. There, the peaks and the troughs will become sharper, and it will occupy more space on our axes. Let's have a look at stretching then. If I wanted to stretch this point here, which is a value of 1, up to 2, I'd have to multiply the sine wave by 2. Now, what's it going to do to the rest of the wave? Well, 2 times 0 is still 0, so this point is going to remain the same. Again, 2 times 0 is 0, this point will remain the same. And this point here, which is at -1, well, 2 times -1, this should sail down to here. So let's see whether that's true by displaying the curve, and this curve is going to be 2 times sin x. And there it is shown in orange. And just as predicted, the point 1 goes up to 2, the point 0 remains 0, and this point here, which used to be -1, has gone down to -2. So I can demonstrate what happens when we change that 2 on this slider here. So there is no change. 1.5, 2, 2.5, 3, 3.5, 4.5, etc. Do notice that the 0 points do not alter. And this curve's worth a brief look at. Here we've actually reduced the curve. So we've said we only want 0.5 of the curve. So our 1 point has come down to 0.5. The second vertical transformation that I mentioned earlier was a shift. So we don't want to multiply the curve by anything. We just want to add a number to the curve such that every point on the curve will shift up by the same amount. I'm about to add 2 to the curve. So this point will go up to 2. This point, which is 1, will go up to 3. This point here, again, 0, will go up to 2. This point here, -1, will go up to 1. So here is the waveform. And as predicted, the 0 has gone up to 2. This point at -1 has gone up to +1. And here is the algebra for that curve, that y now equals sin x, the original curve, plus 2. And you notice that the adjustment is outside the sin x waveform. We've just added 2. So let me show you again what happens when I vary that 2. If I reduce it to 1, the curve now is just 1 unit apart from its original. If I don't have any variation, I get the original. -1, -2, -3. I suppose the crucial point to note here is the curve doesn't change its shape, it just moves up and down on the axis. So let me put both those two curves back on as a comparison. The orange curve is just the original curve multiplied by 2, and the green curve is the original curve with 2 added to it. And those are our two vertical transformations. So for me, with a background in electronics, I think of the orange curve as gain or loudness. Okay, let's turn both the vertical transformations off now. So what are the horizontal things we can do with this curve? Well, the first is that we can shift it to the right or to the left, and we could also stretch it horizontally from a fixed point. If I put the vertical transformations back on again, look where our adjustment of 2 is in the equation. Here it's a multiplication of the wave shape, and here we've added 2. And that's why they are vertical transformations. They're effectively altering the y values all the time. This time multiplying the y values, this time adding to the y values. So when we do a horizontal transformation, we've got to alter x itself within the bracket. And this is where some complications and odd results pop out. Well, I'm first of all going to multiply the x inside the bracket by 2. What do you think is going to happen to the shape of the curve? Now, because we're multiplying, it's likely to be a stretch thing. And you'd be right. But which way is it going to go? Let me turn it on and show you. So the thing to note about it is that where the red curve here completed one cycle in 360 degrees, the purple curve completes, oh, there's the first cycle, 2 cycles. In physics terms, it's gone up in frequency by a factor of 2. I think when you first see that, you'd think that's a bit of an odd result. Here I am multiplying x by something. I'd expect the curve to stretch out along the x-axis. But in fact, it squishes in. I should show you what happens when I vary the 2. Going up to 3, going up higher and higher and higher. And if you count quickly enough, the purple waveform is doing 12 cycles, where the red wave only did 1. And if I go below 1, the wave stretches out. So to achieve any form of stretch, whether that's a positive stretch or a negative stretch, we've put a multiplying factor next door to the x. Now to achieve a push, either to the right or to the left, we have to add something to the x. I'm going to add 90 degrees to x. So I'm going to push the wave by 90 degrees. Now what shape's the waveform going to be now? Let's turn off our stretched one and turn on the answer. So did you guess it would go that way? This peak at 90 degrees here has moved back to now be a peak at 0 degrees. So the curve has actually shifted left, even though the algebraic expression here has a plus. So let me show you what happens when we alter that 90. Let's move it back to 0, where there is no change of shape. So if I now start increasing that amount that we add to x, the curve starts moving left. Okay, if I return to 0, if I now subtract an amount from x, the curve will move to the right. And there we are at x minus 90, and the curve has moved to the right by 90 degrees. Here is the original peak at 90, and the new peak is now at 180. So if I keep on increasing that negative amount, I will eventually shift the whole curve one cycle, and it will sit on top of the original curve, but now one cycle out of place. So those studying physics would see that as phase, a phase difference between the two waveforms. So that's probably one of the biggest elephant traps in the whole of GCSE, in that if you add something to x and then take the sine of it, the curve moves to the left. I think on first sight again, you'd expect that curve to move to the right, but in fact it doesn't. So these are the 4 transformations of that red curve. Yes, I know it looks like an explosion in a spring factory, but it all makes sense. We've looked at the 2 vertical transformations, a push upwards or downwards or a stretch, and the 2 horizontal transformations, a stretch or a shrink, or a move left or right. Again, I would urge you to download GeoGebra and have a go loading this particular application, and you can change the function and you can see what happens to different wave shapes when we apply the 4 transformations we've looked at.